Stanford University.
So let's begin. I'm going to review very quickly, I hope quickly. We described a simple system consisting of one qubit. I'm going to change my terminology a little bit. I'm going to start calling that qubit a spin. Don't worry about what it has to do with spinning at the moment. Of course, more important is that it's a little pointer. Now, I use the term pointer. I began to use the word pointer to refer to vectors in three-dimensional space. While I was writing, I realized that that's an awfully awkward and unfamiliar terminology, and I decided to replace it with another term, the standard term, three vectors, vectors in three-dimensional space. I may sometimes use the term pointer, but I think I'm more likely to speak of three vectors. And a three vector means a vector in real space. The more general concept, when I simply say vector, more likely I'm speaking about the abstract notion of a vector space and the elements of a vector space. Just to warn you and keep the language clear. Now, we talked about this qubit, which has now become a spin. It has some of the character of being a little three vector in space. There is some sense or other in which it points in a direction, and that we can confirm by an experiment. As was said before, once we start thinking about quantum mechanics, we really do have to think about systems and their connection with apparati. Is that a word? Apparati? I'm not sure. Apparatuses? Apparatuses? I'm not sure what the plural. Apparatus? Anybody know the plural of apparatus? Apparatus. Oh, just apparatus? Okay, just apparatus. We do have to think about the connection with their apparatuses that measure them. And we don't get away with just ignoring it. What's the difference? First of all, I'll tell you what the basic difference is in classical physics and quantum physics. In classical physics, measurements can be arbitrarily gentle. Arbitrarily gentle means that you can find out anything that you want about a system in principle by interacting with it with something that changes anything about it by an arbitrarily small amount. For example, you want to locate the location of a particle in classical physics. How do you do it? You shine some light on it. You shine some light on it, and you make an image. Of course, you have to use light which is small enough wavelength that it can resolve the object. This is true, but there's no limit to how weak a light signal can be at a given wavelength. You can make the light signal as weak as you like so that it carries as little energy as you like, as little momentum as you like. Let it interact with the thing you're interested in, form an image, and then after that image has been formed, it can be magnified, not magnified in the sense of making it bigger, but what's the right word for amplified? It can be amplified. And so the experiment itself can be arbitrarily gentle and still find out anything you might want to know about the system. The result of that is an experiment can always be done which has no effect whatever on future experiments, on subsequent experiments done, for example, right afterwards. That's classical physics. Quantum physics is not like that. Quantum physics is such that experiments inevitably change systems. Any experiment to measure something will change something else. It's almost as though the experiment to measure coins was such that every time I looked at the coin jumped up in the air and randomly flipped itself. We know that doesn't happen, and we can measure the state of the coin gently without changing it. Quantum mechanics, not so clear. Well, it is clear. It's clear that that cannot be done. Okay, but we're going to talk a little bit, before we move on to more about vector spaces and operators and the mathematics of quantum theory, I want to talk a little more about the logic of it and in what way logic in quantum mechanics is different than logic in classical physics. Let's go back to our spin and our apparatus. The spin is I'll draw it as a little arrow. Whether it truly corresponds to anything that looks like a classical arrow or not is irrelevant. We have to draw it on the blackboard, and anything I draw on the blackboard will be classical, just because ink and pens are classical, or approximately classical. And an apparatus. The apparatus is a window that has a number that comes out of it. Number appears in the window, tells you the result of the experiment, and it also happens to have a direction in it which tells you which side is up, how to orient it. In fact, it might have a whole set of 3 axes that tell you how to orient it. But that's not important. Just the up axis is what's important. And when the apparatus is pointing up, in fact, no matter what direction the apparatus is pointing in, when it interacts with the spin, it produces a number in the window, and that number in the window is either +1 or -1, no matter what direction the apparatus is pointing in and no matter what has happened to the spin beforehand. When the apparatus is pointing up, we will say that what it has measured is the z component of spin. Let's put some axes in here, z up, x to the right, and y out of the blackboard. And when the apparatus is pointing up, we'll say that it produces an experimental number which measures the z component of the spin. Yeah? Now, is that particularly interesting to think of it as having a directionality? When we say it's a z component of the spin, we're imagining that this object here has a sense of directionality to it. How can we test if it has a sense of directionality to it? Well, we can prepare the spin in a state of what we think is pointing up by simply letting it interact with the apparatus. And when the apparatus appears with a +1 sign in it, we'll say, aha, the spin is up. If we do it again with the same apparatus pointing in the same direction with the same spin, we'll get up again, and up again, and up again. In that sense, quantum mechanics allows for reproducible experiments. If you measure the same thing several times in a row with the same apparatus, you will get the same answer over and over. So things are not that weird. And that's awfully important because we have to have some concept of reproducibility of experimental results in order to make any sense out of things. So this is a good thing. When you measure something and you measure it again and again and again, you get the same answer. Yeah.
So how does that fit in with what you just said?
We're going to come to it. We're going to come to it. We're going to come to it. Well, I didn't say that experiments are necessarily so ungentle that when you measure anything, you affect everything. The answer is you affect some things. In this case, when you measure something, you don't affect that same thing. If you measure it again, the same thing again, you'll get the same answer. Okay, now you could then say, all right, now that I have detected that the spin is up, let me turn the apparatus completely over and point down. If this were a thermometer measuring the temperature, I don't think we would expect it to measure minus the temperature if we turned it over, right? No, not if it was any kind of decent thermometer. So we would therefore say that the temperature does not have a sense of orientation, certainly not in this sense. On the other hand, if this is a true spin and we turn the apparatus over, if initially the apparatus told us that the spin was +1, after we've turned it over and do the experiment again, it will register -1. So it seems to indicate that there is a sense of directionality. And of course, yeah. The same thing is true no matter what direction we hold the apparatus in. If we hold the apparatus in the horizontal direction, and come along and detect a spin that we know nothing about. We have not yet made a measurement on it. Maybe somebody else has made a measurement on it. Maybe some agent unavailable to us who, some secret person has done something to that spin, but we don't care, we don't know about it. We come in with our detector and we make a measurement. What will we measure? Again, we will measure +1 or -1. And if we're beginning to think of this thing as having a sense of direction to it, we might say that what we're measuring now is this x component of the spin, whereas previously we were measuring the z component of the spin. Let's give them names. The sigma z, which is the component of the spin along the vertical axis. At the moment yet, I'm not asking you to think that the notion of component is the same as the notion of component in classical physics. It's just a name for the moment. And sigma z, whenever it's measured, is ±1. The same thing happens when we turn the apparatus on its side and we measure the same procedure. We measure something that we can now call sigma x. And sigma x is always ±1. And the same thing if we turn the apparatus around so that it's facing frontward. In fact, no matter what direction we orient the apparatus, it always gives us ±1. This would be a little bit strange, more than a little bit strange, if this object really were a classical vector, a little vector, perhaps a vector of unit length. If it were a vector of unit length, and this detector were really measuring the component of spin along its own axis, there is no way that it would just give ±1. Right? Components of vectors, even if the vector is required to have exactly unit length, here's a vector with exactly unit length, a pointer, a 3-vector of exactly unit length. If we turn it and do other things with it, the x component or the z component can be any number between -1 and 1. So this is a funny vector if it's a vector at all. But still, it does seem to have a sense of orientation. The results of experiments do seem to change when you rotate detectors. In particular, if you begin by orienting the spin along the z-axis in the up direction, let's call this up, that means sigma z is equal to +1, and then rotate the apparatus, detect it again, you won't necessarily get +1. In fact, you may get +1 or you may get -1 with equal probability. You could do the experiment over and over and over again. Half the times you would get sigma x equals +1, half the times you would get sigma x equals -1, even though you knew sigma z was exactly +1 in each case. So something's funny, but what is true is that the average value of sigma x will be 0 if the initial starting point was a spin that was up along the z-axis. Same for the y-axis. If the initial value of the spin was prepared to be up along the z-axis and you rotate the apparatus into the y orientation, again, you'll have equal probability. And so the average value of sigma y will be 0. You can even go beyond that. You can say, let's start with the apparatus, not vertical, but let's start with the apparatus along the x direction. Use it to prepare the spin so that it's known to be pointing horizontal along the x direction. In other words, sigma x is equal to +1, and then do a y or z experiment. Always, we will get random but equal probabilities for up and down, or plus and -1. You go a little bit further. Now, of course, I am quoting what would be the results of experiments on spins. I've never done such an experiment. I don't think I could. But I have no doubt that if I had the skill to do it, this is what would happen. What?
Suppose we start out and we have not prepared the spin at all.
Doesn't matter. Okay, go ahead.
So it could be up or down or X or Z, Y or Z.
Right. We don't know we don't know what it's past.
We don't know what it is.
Right.
And we set it up so that the apparatus is on its side along the x-axis.
Okay.
And we do lots of measurements. We get it. What's
Well, we first do one measurement before we do anything else. Yeah, let me come back for a second. Let me come back a second.
Okay.
you're right, we want to do a lot of experiments and a lot of measurements in quantum mechanics. There are two distinct ways we could do lots of experiments. It really doesn't matter which we do. We could imagine having a large number of identical spins prepared at the beginning, however they were prepared. And we can do experiments on a large number of them, or we can do repeated experiments on the same spin. To a large extent, it doesn't matter which we're talking about, and I'll tell you when it matters. But at the moment, all we're talking about is one spin. You said start the apparatus horizontal, stick the spin into it, and detect what you get. What you get will either be +1 or -1. Okay? You could then take the spin out of there. Give it to your friend who does some magic with spins. You don't know what it is. You don't know what the hell he does with it. He flips it around, juggles it, puts it in his pocket, takes it out, and gives it back to you, and tells you to do it again. Again, you'll get +1 or -1. It may be that he did nothing, in which case the second time you'll get the same answer you got the first time. Or it may have been that he turned it over, in which case you'll get the opposite answer. But whatever you get, it will be +1 or -1. Then if you do a repeated experiment, knowing that nothing else was done to the spin in between, you'll get the same answer if you do the same experiment. Okay? That's good. Okay, so let's be a little more general. Let's suppose that we orient the axis of the detector in any direction. So let's make a notation for a direction, a unit 3 vector. A unit 3 vector. Unit vectors in three-dimensional space are always indicated by putting a little hat on top of the symbol. So this is a unit vector along a particular axis. We start with our detector along the axis M, not horizontal, not vertical, not in or out, but just catty-cornered in some complicated way. There's M. There's M. And we start with the spin. Let's start with the spin previously having been oriented or prepared along a different axis, the N axis. How do we do that? Well, I should have gone a little slower. We start with the detector along the n-axis. Do an experiment and discover that along the n-axis, the spin comes up +1. Then we rotate the apparatus into the m direction, and we do another experiment on the same spin. It will either come up +1 or -1 along the m-axis, never in between, but the average value of the spin along the m-axis here will not be 1. It will not be -1. What will it be? It will be the cosine of the angle between m and n. In other words, the component of m along n. How do we write that? Let's write that. Let's write a formula for that. The symbol for averages in quantum mechanics are a pair of angular brackets like this. This one is called the bra, this one is called a ket, and the whole thing makes a bra-ket, which is British for bracket. Okay? The average value of sigma m, knowing that it was originally oriented along the n direction and measured along the m direction, is the cosine of the angle between n and m, which can also be written as n dot m, the ordinary dot product of the vectors, or just the component of n along m. The spin was oriented in the n direction, you measured it along the m direction, and the answer is ± 1, but on the average, it's what a classical physicist might have expected if he measured the component of a spin which is oriented in one direction along some other direction. This is exactly the component of m along n. All right, so if you do the experiment many, many times and collect averages, it seems, in fact, that the average quantities do behave like vectors or like 3 vectors. But the individual experiments are very resistant to giving any answer other than plus or minus 1. Okay, so this now,
The apparatus doesn't know how, the apparatus doesn't know how to give any answer other than plus or minus 1.
doesn't know how to give, well, doesn't know how to give any. You might try to build another apparatus that does better, but it won't do better.
To make sure I understand the setup here, the setup is that you prepare the
spin along the n-axis. And then you measure it along the m-axis. Right. And you get a random answer, but random biased. Biased in such a way that the average is n dot m. That, for example, would mean that if n and m were the same direction, that you didn't rotate it at all, what is n dot m in that case? 1. All right. And that would just be an indication that you got the same answer if n was up, and you did the experiment, you'd get it up and up and up over and over and over again. Okay.
Wouldn't it be more, I want to be very rigorous here, wouldn't it be more accurate to say the expected value would be n times n rather than the average?
No, no, no. My friend Murray Gell-Mann loves to say the expected value. It is not the expected value. If I gave you a probability distribution which looked like this, what would be the expected value that you would have? The least expected value would be the one right in the middle, but the average value would be the one right in the middle. Okay? Expected values and average values are very different in general. And this is the average value. The average, if you average the quantity that you get in the standard sense of averaging, standard average. It's also called the expectation value. But again, that's a misnomer. It's not the value that you expect necessarily.
Just want to make sure I'm thinking about this right. The spin, the only thing we know about the spin is that when we measure, we get plus 1 or minus 1.
Right.
That's all. Really, that's all.
That's all. Well, that's all we know until we start doing a lot of experiments.
About the z component of this and that. That all has to do with results
Which way
we got from the apparatus.
That's right.
Has nothing to do with the thing. I mean,
Well,
at least a priori.
Well, there are different experiments that you can do on the spin. The results of those experiments can be used, or the particular experiment you do can be used to label what it is that you measured.
I guess the point I'm trying to make is at one point you were drawing a spin as having an arrow either up or down, and that seems to be sort of prejudiced. It's either plus 1 or minus 1, whatever that means. We don't know. There's no
Right.
geometric meaning to it.
Yeah, that's right. There's no geometric meaning to it, obviously, to begin with. But we did discover that by turning this thing over, we always get the opposite sign. Well, that's starting to tell us there's some difference between the apparatus up and the apparatus down. It's not like a thermometer measuring temperature. There's some notion there that it's different to be up and down. And then if we turn it on its side, we find out that in some sense it really does behave on the average like a vector. On the average. Okay? But it is what it is.
But that vector changes depending on how it's been prepared. In other words, when you prepare it, you may have something with an x component if you've got the apparatus one way, but if you prepare it with the apparatus another way, it may have a z component. Is that correct?
Yeah.
Okay.
Yeah. But it is what it is, and I've told you the facts. The facts are, if you first prepare by putting your apparatus along one direction, and then measure with your apparatus along the other direction, the average value of the result will be n dot m, but every single event will be a +1 or a -1. Nothing left to say.
But something
Say it anyway.
That's slightly different is that if n and m are along the same direction or opposite direction, then it isn't just an average, it repeats itself.
Yeah,
Whereas if it's any of the others, it's an average.
yeah, right,
It's still an average, right? Get the same.
right. But if a number or a result can only be plus or minus 1, and the average is +1, it means every event was +1. Right. Okay. Let's talk about logic a little bit. Our problem with quantum mechanics is that logic, the logic of quantum systems, is different than the logic of classical systems. But our brains are classical systems and incapable of thinking in quantum logic. Nevertheless, we can get a glimmering of what quantum logic is like by thinking about these experiments. We could either talk about the calculus of propositions or the nature of the states of a system, the space of states of a system. Let's start with the space of states of a system. The space of states of a system, and think classically for a moment, they're a set. And they're a set of possible states. Here they are. Heads, tails, 6, 5, 4, 3, 2, 1 for the die. Particle on a line would have an infinite number of possible states, but the states form a set of some type. A proposition about the states of the system is basically a subset. It's the subset of states for which the proposition is true. Okay? So for the die, my proposition is the die shows an even face. That's a proposition, and it's true for half the states of the die, and so it corresponds to a subset, 2, 4, and 6. Right? There's the contradictory statement, the not statement. Not the die shows an even face, which is obviously equivalent to the statement the die shows an odd face. And so in classical logic, the not of a statement, the not means the contradiction of the statement. If this is the statement, meaning to say it's true for all the subset of states in here, the not statement is the statement, is the complement or the collection of things which are not in there. Okay, let's go to our spin. Proposition, the spin is up along the z-axis. What's the not of that? The not of that is if we measure the spin along the z-axis, we get something else other than 1. The only other possibility is -1. So spin equal -1 along the z-axis is the not statement of the spin is up along the z-axis. So logic makes some sense, but we begin to find very peculiar differences when we start talking about the operations of combining propositions through the use of and or. And or are different in quantum mechanics than they are in classical mechanics. I want to lay that out. It's so interesting and so rarely explained that I sort of like to explain it. Yeah.
I may be reading in what's not there, and if I am, just correct me. In the classical example, like the dies, the universal set is finite in terms of the number of elements in it.
Number of states in it.
And then you jump to the quantum example, and it seems like that would be infinite because of all the possible times. Does that make a difference?
With all the possible what?
All the possible experiments that you could do is not limited.
Yeah, okay, you're getting at something important which we're going to get to. It's clear that in some sense the number of states of this spin is finite. It's just up or down if we measure it along the z-axis. On the other hand, it also looks like we can tilt our apparatus in any direction and prepare the state in any, oriented along any direction. So it looks like there's an infinite ambiguity in the state of a system. This is the whole point of trying to understand the states of systems, to understand the connection between the continuously different direction that the electron could point in and the fact that any time we measure it along a given axis, it's only up or down. But we'll come to it. It's a good question, but we'll come to it. Okay, let's talk about calculus of propositions. If I give you two propositions, A and B, I can form two combinations of them, A or B and A and B. Let's just see what that means in terms of sets. If we have two propositions, this one is A, this one is B, then A and B means the set of states which belong both to A and to B. Right? So it's the intersection of the set A and the set B. Called logically the intersection, or set theoretically the intersection, is basically the AND operation. This point is in A and it's in B. Okay, that's straightforward. Given any two propositions, you can always form the, or another way to say it, the right way to say it, is this is the set of points in here for which the proposition A and B is true. A and B is true in here, and it is true nowhere else. Okay. What about these two subsets, A and B? A and B is still a proposition, but it's always false. There is no state for which A and B is true. All right, so there are A's and B's that you can put together. I mean, my friend Sanjay over here weighs 600 pounds, and my friend, that's not a good one. There are combinations for which A and B is always false, obviously. All right? In particular, if you take A and not A, it's always false. All right, but still, the definition of A and B is the intersection, and it's true for all the states in the intersection. OR is a little more complicated, or at least there are two versions of OR. There is the exclusive OR and the inclusive OR. In the English language, we usually, when we use the word OR, we usually mean the exclusive OR. When we say that I am Jewish and I am Catholic, or I am Catholic, I ordinarily mean that I can't be both, right? That I can't be both. And so the usual OR is the exclusive OR, the one you normally think about. But in logic, the term OR is the inclusive OR. It means A, it's true if A is true, it's true if B is true, and it's true if both of them are true. It's the inclusive OR. So I can correctly say I am a physicist and I am a father. That's true. But I can also say I am a physicist or I am a father, and it is also true. Why? Because both of them are true. So that's the inclusive OR. Inclusive OR corresponds to the union of two sets. If I have A and I have B, then the inclusive OR is everything in both sets, or either set. Okay, anything, not in both sets, anything in either set or in both sets. The exclusive OR would correspond to things in one set, but not the other set. The exclusive OR includes, we will always, whenever I speak of OR, I always mean the inclusive OR. Okay, so that's AND and OR. What else can you say about them? Not very much. Yeah, we're going to now use that concept to try to formulate a set of and or statements about the spin, and then ask, how would you verify them? How would you verify them? How would you verify them, and does it mean anything to verify them? Okay, so let's take the two propositions, A and B, to be sigma z is equal to plus 1, and sigma x, this is A, and this is B. Sigma x is equal to plus 1. They're both propositions. We would know how to check either one of them. If we wanted to check sigma A, so the first A, we would turn our apparatus vertically upward and measure the spin, and we would check it. It's either true or false. If we wanted to find out if B was true or false, we would turn the apparatus on its side. All right? In classical logic, if there are two propositions, you can form the combination A or B. Let's start with A or B. So we'll take A or B. And let's think about checking its truth value. Is it true or is it not? All right, so we'll design an experiment to try to, and let's go back a step. Let's imagine the hidden ghost in the works has previously, unknown to us, has originally oriented the spin upward along the z-axis. He knows, we don't. As far as we know nothing, but the ghost in the works has oriented the spin vertically upward. And this doesn't matter, but we could start that way. So the spin is upward, and let's check whether A or B is true. How do we begin? Let's begin by measuring the spin along the z-axis. We put our detector or our apparatus in the vertical direction, and we measure. What do we get? We get plus 1. We get plus 1 because the ghost in the works has made it a point to begin with. We don't have to go any further. A or B is true. A or B includes the possibility that both A and B are true, but all it requires to be true is that one of them is true, and we've just discovered that A is true. So A or B is definitely true. But now let's do the experiment in another way, in an order which would not matter if we were doing classical physics. And the reason it doesn't matter when we do classical physics is when we do an experiment that has no necessary effect on the outcome of a later experiment, if the experiment is gentle enough. So let's do the experiment in the opposite order. Instead of first finding out whether A is true, let's first ask if B is true. And then we'll come back and ask if A is true. All right, secretly the spin is pointing up in the z direction. So the ghost knows that, but we don't. And so we come along knowing nothing about this spin and say, why should I measure A first? Let's first measure B. Let's first measure the x component of the spin, and what do we get? We get either plus 1 or minus 1. We get plus 1 or minus 1 with a 50% probability. So there's a 50% probability that B is plus 1, but if B is not plus 1, it doesn't mean that A or B is wrong. We still have the chance that when we measure A, it'll be plus 1. Okay, but the problem is that in measuring B the first time around, we prepare B along the x-axis. Whatever we get, whether it's this way or this way, we have prepared that spin along the x-axis. What will the next experiment give when we measure it along the z-axis? 50% probability of being up and 50% probability of down. That means we have a 25% probability of finding both that sigma x was equal to minus 1 and sigma z is equal to minus 1. We have a 50% probability in the first experiment that sigma x was not equal to 1, and then in the next experiment we have another 50% probability on top of that that sigma z was not equal to 1. So we have a net probability of 1/4 that both A and B were false when we did the experiment in one order. When we do the experiment in the other order, it is certain that A or B is right. Why? Because A is right. So, what is true in classical physics, that the idea of A or B is symmetrical between A and B. The idea of the or statement, A or B, if A or B is true, then B or A is true. And we find that in quantum mechanics, the concept of A or B at best can only be defined in a way that depends on the order in which you determine A or B.
I mean, I would say that the two propositions are incompletely specified in the quantum mechanical case, because you have to give the order, right? It isn't like the particle has a certain X spin
Yeah.
independent of how you handle it, right? Would you say that's right?
Yeah, I would. But I would also say that any attempt to think of a logic of experiments will be different than quantum mechanics.
What's the hierarchy between A and B?
Why the what?
Hierarchy.
What hierarchy?
In other words, A and B, if you measure A, then you're certain of B. If you measure B, then you aren't certain of A, but you're certain.
No. Let's go back. I said the ghost in the woodwork has made the spin to be pointing up along the z-axis. We don't know that, but it's true, okay? Then if we measure sigma z first, under those circumstances, we will surely find that A or B is true. But if we measure under the same circumstances, the same degree of lack or presence of knowledge, we measure B first, we find out that there's a 25% chance that A or B, this composite statement here, is false.
So a question, the operation A or B, the result is now going to be a probability. It's going to be 0.25 instead of 0 or 1.
Well, not only that, but you have to specify which order you determine A and B, right? So that's in itself an element of something new, that the or statement does not unify two statements into a symmetrical, in a symmetrical way.
Question? I'm confused when we, the thing has been prepared so that it's up. We don't know if it's been prepared.
Yeah.
We then.
You know, that didn't matter. Just to simplify the story, I said that. It wouldn't have mattered if
But we then do the experiment. We do B, we test it by turning the machine, the apparatus on its side. And I thought what you had said is, if we now do this multiple times, we'll get an average.
Yeah, but we're not doing it. We're trying to find out.
But you're saying we're going to prepare, what you're saying is, when we do that first measurement on its side, we're preparing the spin again. And that would say then from then on, we should always get +1 if we prepare.
+1 for sigma x, but then if we do sigma z, we'll get a random answer. Measuring one,
But you said
random.
we're going to get a random answer for
Sigma z.
the first measurement of sigma x.
Yes.
Think about it. I can't stop the class to.
Okay.
Question, if we have a measurement device to measure two different particles, and
Why have you jumped to two particles?
I was just wondering, the act of measurement, does it inductively spread backwards?
What?
Uh,
Okay. That was all review. All right, the next thing, which I was going to review, but I'm not going to because it took too long, is vector spaces. I'll just remind you real quickly. Vector spaces are sets of elements. You can add elements. This is not something you would do with sets. You can add two sets, of course, to make a bigger set, but there's no natural single element which is the sum of two elements. So the elements of set theory, namely the basic individual objects, are not things that you can add and make new elements. The space of states of a quantum system is a linear vector space, and that means given any two states, you can add them in some sense and make another state. And that's what we're going to explore. This logic, this peculiar logic and this peculiar distortion of logic turns out to be the logic of vector spaces. It's a logic which is embedded in the structure of vector spaces in a very neat and tidy way, and that's why, ultimately, why vector spaces are important. Okay, so let's just remember vectors are things that you can add. If there are two vectors, A and B, you can add them. You can multiply them by complex numbers. Every vector has a dual vector, which is kind of its complex conjugate. If we call these objects ket vectors because they are the second half of a bra ket, then the ket, the bra vectors, which are in one-to-one correspondence, which are for every ket vector, there is a bra vector, but its status is that of a complex conjugate. So there's two dual vector spaces, and you can take inner products of vectors, a bra vector with a ket vector. Okay? So the bra vector and the ket vector can be combined together. It gives a complex number. The inner product is a complex number, and it satisfies that it is equal to the complex conjugate of the opposite order. So when you take a complex vector in a complex vector space and you take the inner product, if you interchange the two vectors, then that's equivalent to complex conjugation. That's pretty much what you need to know. That allows you to define, given the idea of an inner product, it allows you to define the notion of the length of a vector. We usually don't think about the length of the vector, we usually think about the square of the length of the vector. And the square of the length of a vector, let's say the vector is A, is the inner product with its own conjugate, or with its own dual. Usually we say it's the inner product with itself, but that's a sort of slight abuse of terminology. And this is always real. The reason it's always real is because if we interchange A and A, we just get back to the same thing, but this tells us that the inner product of A and A is its own complex conjugate. Being its own complex conjugate, it's real. It's also positive. That's easy to prove. And it can be thought of as the square of the length of a vector. It's analogous to, closely analogous to, the dot product of a three vector with itself. If A and B were three vectors, then we wouldn't distinguish the bra and the ket, but we would write that A dot B is the dot product between two vectors, analogous to this. And we would also write that A dot A was the square of the length of A. Okay? So the inner product of a vector with itself can be thought of as the square of the length of the vector. And finally, there is the notion of orthogonality. Two vectors are orthogonal when their inner product is 0. Orthogonal. Same definition as for dot product. When the dot product between two vectors is 0, those vectors are orthogonal. Those are the definitions that we need for a vector space. The other definition is the definition of the dimensionality of the vector space. How many dimensions does a vector space have? And the way to decide that is by asking what's the maximum number of orthogonal vectors that you can find in the vector space. For ordinary vectors, let's say in 2, 3, 4 dimensions, this is obvious. In 2 dimensions, I can pick a vector. Just pick any vector. Make it a unit vector just by shrinking its length until it's of unit length. And then I look around and I see if I can find another orthogonal vector to it. Yeah, in fact, I can find two. One points this way and one points that way, but that's not an important distinction. We find one other direction or one other vector apart from a numerical multiple. Apart from a numerical multiple, there is one other vector which is orthogonal to it. And so there are two the maximum number of mutually orthogonal vectors that you can find is 2. If you go to 3 directions, you can find a third one, but no more. Try to find a fourth one, and you run out of directions. So 3-dimensional space has 3 mutually orthogonal vectors. 4-dimensional space has 4, and so forth. And the same thing is true of complex vector spaces. We described a version of complex vector spaces which were just column vectors. Alpha 1, alpha 2, alpha 3, ... And their duals, which were row vectors, which were made up out of the complex conjugate variables. And so once we have a vector, we can start looking for orthogonal vectors to it. Vectors which are perpendicular in this sense. Find another one, then look for a third one, look for a fourth one. However many you find, you'll eventually run out of directions. That's the dimensionality of the space. For the special case in which there are only 2 entries here, it's a 2-dimensional vector space. You can only find 2 mutually orthogonal vectors. You can find many pairs of mutually orthogonal vectors. You know, just in a real space, there's these, you point them in any direction, but once you find 2 of them, there won't be another one. Okay, so we have the idea of mutually orthogonal vectors. And now we have to state what is the connection between a vector space and the space of possible states of a quantum system. The quantum system that we're going to deal with is still this very primitive and simple single spin. Until we get the handle on that, we won't want to move to more complicated things.
Is there any restriction that the orthogonal vectors have to be perpendicular to each other?
That's what orthogonal means.
Well, suppose you have a cube and then you sort of tilt it like a parallelogram. It's still 3-dimensional, but the coordinate systems are not perpendicular. One of them is not.
Perpendicular and orthogonal are synonymous terms.
Maybe it's the wrong term, but it has a right angle. You know what I'm saying?
Perpendicular and orthogonal both mean right angle. You're confused by something, and I don't know what it is. Hmm? Yeah, I know you are. But perpendicular, orthogonal, right angles, they mean all the same things.
I think he's thinking of linearly independent versus being really orthogonal. But if you have a set of linearly independent vectors, you can extract an orthogonal set out of them.
This is true. He's not confused. This is right. Linearly independent is different than orthogonal. Orthogonal is linearly independent, but linearly independent is less strong than orthogonal. These 2 vectors like that, they're linearly independent, but they're not orthogonal. Those are orthogonal. Okay, we'll come back. All right, the states of a quantum system, this is a postulate, form a vector space, form a complex vector space. In fact, the space of the simple system we've been discussing form a 2-dimensional vector space. Let's write down some vectors. We know some states. We know, for example, that there is a state that can be prepared in which the spin is pointing upward along the z-axis. We characterize the state by the experiment that we did to get it in that state. That experiment had the apparatus vertically upward, and it created a state of the system which either could have been down or up, but let's say it's up. Right? We can label that state in a number of ways. We can call it up, we can call it down, we can call it plus, we can call it, well, up and down are the same as plus and minus. We could draw them with little arrows, up and down. What other ways could we? We could write it as sigma z equals +1, and sigma z equals -1, they all mean the same thing. Up, down, plus, minus, sigma z equals +1, sigma z equals -1, all the same thing. All right? So there are two states that we know about that we can access by putting or we can prepare by turning our apparatus upward along the z-axis. Let's give them names. These states are vectors in a vector space according to hypothesis, and they can be called, let's say, up and down. If it is true that the vector space is as simple as just a two-dimensional vector space, then that means that any vector in that space can be written as some linear combination of up and down. In other words, every vector in a two-dimensional space can be written in terms of two basis vectors, up and down. So that's enough to write any state, whatever, up, down. All right, what about, though, the state which is made by tilting our apparatus along the x-axis? We get something different. It's not the same thing. It's not up, because up means up along the z-axis. It's not down, because down means down along the z-axis. And we know they're different because we know the results of experiments on these two different kinds of states will in general be different. So we can call those states, I tend to call them left and right. There's up and down, there's right and left. Those are two other states. We could draw them this way if we liked. They also correspond to sigma x equals 1 and sigma x equals -1. And we could label them if we liked. Let's label them right and left. Finally, we know that if we were to turn our apparatus so that the apparatus was pointing along the y-axis, we could access two more states. I think we call those in and out, into the blackboard and out of the blackboard. And so there's in and out. Into the blackboard and out of the blackboard, and they correspond to sigma y equals ±1. We could label them in and out. All of the logic that I've described to you and all of the experimental results, as we will see, we will not see it immediately. It took some time to understand all of this. It is all summarized by a few statements, but the first of which is that the space of all states of that simple system is two-dimensional, has only two independent states, which means that these other things can be written in terms of up and down. Okay, so let's go to general linear combinations of up and down and ask what they mean. Let's take a vector, I guess we can call it A, which is of the form a coefficient, a complex coefficient alpha 1 times up plus another complex, I suppose we should call this alpha up, alpha down times down. The alphas are complex numbers. In complex vector spaces, you multiply, they could be real numbers, but in general, they will be complex numbers. Let us suppose we knew what that meant, what kind of state this was, where it came from. It's a new beast. It's not up, it's not down, somewhere's in between. Next postulate. The next postulate is that if we were to measure up and down, if somebody prepared us an electron or a spin in this state and we measured up and down, we would find probabilities for up and down, and those probabilities would be probability for up is the square of the magnitude of this coefficient, and probability for down is equal to alpha star down alpha down. In other words, it's basically the square of the coefficient or the square of the component of A in the directions up and down. These alphas, they're essentially the components of a general vector along the two axes up and down. There's something that I failed to tell you. It's also a postulate. There are many, many postulates, but you'll see they fit together in a neat package. There are probably fewer postulates than I'm saying. I'll bet we could reduce it down to 4 postulates, 4 axioms. But rather than try to axiomatize it, we'll just do it a little more informally. What's the relation between up and down? Are they the negative of each other? No, they're orthogonal. Now, that's a postulate. The basic postulate is when things are measurably different, when two states are such that you can cleanly tell the difference between them by an experiment, they are orthogonal. Orthogonality literally means they are sufficiently different that you can, with a single experiment, tell, or maybe a few experiments, tell the difference between them uniquely. I'll tell you what it corresponds to in terms of sets. You might say that two sets are orthogonal if they don't share any elements. This is not a standard terminology, but you might say it anyway. They're orthogonal if they don't share any elements. That means they're distinctly different. There's no chance that an experiment will confuse the two of them. The experiment will, a nice experiment to distinguish them will not lead to any ambiguity. The same is true of up and down. Up is distinctly different than down. If you measure up, you'll measure up again and again and again. And the version of that in quantum mechanics, or the implication of that in quantum mechanics for the vectors, is that things that correspond to physically unambiguous different situations are orthogonal to each other. So up and down are orthogonal to each other. What if we have a combination of up and down with some coefficients? Then there's a probability to be up and a probability to be down, and the probabilities are given by alpha star alpha up and alpha star alpha down. Again, that's a postulate, but we'll see in a moment what that corresponds to. Well, what's the relation between the probability for up and the probability for down? The answer is that if we add them, we get 1. And therefore, alpha star alpha plus beta star beta is equal to 1. Any reasonable state of the system which has total probability 1 for all the different things that can happen should satisfy that the sum of the probabilities, of the distinct probabilities, should add up to 1. And so that says that alpha star alpha plus beta, not beta, alpha up up plus alpha down star alpha down. Did I use beta before? No, okay. Should equal 1. But that's equivalent to the statement that the inner product of A with itself is equal to 1. When we think about it, prove this. Prove that alpha star alpha summed over up and down is equal to the inner product of A with itself. It does follow from the postulates. It does follow from the postulates and the assumption that U and D are perpendicular unit vectors. U and D are perpendicular unit vectors. Make that assumption. They're orthogonal to each other. They're unit vectors. If they're not unit vectors, you can change them until they are unit vectors. And then you can prove that the inner product of a vector with itself is just the sums of the squares, or the conjugates times itself. Okay, so that's a little thing to prove. But what does that say? That says that a physical state corresponds to a vector in the vector space of unit length, a unit vector. The unit standing for the fact that the total probability is 1. All right, so states not only equal vectors in a vector space, but they're unit vectors. The other term for unit vectors is normalized vectors. Normalized vectors. Normalized is another word for unit. So all physical states, all states of what you can do to that electron spin or to anything else correspond to unit vectors. And given any such unit vector, the probabilities associated with it are alpha star alpha up and alpha star alpha down. Right? So that is a bit of information. But wait a minute. What happened to these other vectors right and left? What happened to right and left? Right and left seem like different states. But according to the postulate, right and left must be linear combinations of up and down. That's not too surprising, because if you prepare right or left and then measure up or down, you get +1 or -1. That's all there is, +1 or -1. So it's not too surprising that whatever right or left is, it's somehow a combination of up and down. And that statement is buried in the properties of vectors. So let's look at the state left. No, let's look at the state right. What do we know about it? Well, we know that it must be a combination alpha up, up, plus alpha down, down. We can also write that in the form of a column vector, alpha up and alpha down. Number one. Number two, supposing an electron is created pointing along the right direction, the x-axis. What are the probabilities for it to be up and down? You remember? Half. Half. That means that alpha up star alpha up must equal a half, and alpha star down alpha down must equal a half. Okay. Let's make a guess. Let's make a guess. The simplest guess would be to put 1 over square root of 2 and 1 over square root of 2 here. Alpha up is 1 over square root of 2. If alpha up is 1 over square root of 2, what's alpha star alpha? 1/2. Okay? This one's also 1/2. Now we could put some other things. What ambiguity is there? We could put a minus sign here, or we could put a complex coefficient in front of here without changing the magnitude of it. We'll come back to that. We'll come back to what that means. We'll come back to what that ambiguity means. But let's take this as a working hypothesis for what the state right is. That leaves us with the state left. What do we know about left? Well, right and left are physically distinguishable by a single experiment. You can orient your apparatus along the x direction, measure sigma x, and determine unambiguously whether it corresponds to right or left. What does that mean about the vectors right and left? It means they're orthogonal. Orthogonal and physically measurably distinct are the same things. So that tells us that left, right should be equal to 0. Incidentally, we have assumed that up, down is equal to 0. Up, down, orthogonal, by symmetry, basically. There's nothing different about the x-axis than the z-axis. So if the two vectors up and down are orthogonal, it stands to reason that the two vectors left and right must be orthogonal. Here's right. Is there a vector that's orthogonal to it? Yeah. There is a vector which is orthogonal to it. What is it? 1 over square root of 2 up minus 1 over square root of 2 down. Now, it's ambiguous whether you put the minus sign here or here. Either way will work. And we'll find out that there's no physical difference between those two possibilities. We'll find out later that there's no physics in the overall sign of a vector. So here's one which is orthogonal. How do we check that this is orthogonal to that? Well, let's write the here's the column vector describing right. Let's write down the row vector. No, that's not the column vector. Here's the column vector. The column vector describing right is 1 over square root of 2, 1 over square root of 2. That's these two. What is the row vector describing left? If we want to take the inner product, we want to combine the row vector with the column vector. So the row vector describing this guy over here is 1 over square root of 2 minus 1 over square root of 2. And to take the inner product between them, you take the product of the first coefficient times the first coefficient plus the product of the second one times the second one. Standard rule for taking the inner product between a column vector and a row vector. You match the first component with the first component, multiply them. Second component with the second component, multiply them. And go right down through through all the components and add them up. Okay, so what's the answer? 1 over square root of 2 times 1 over square root of 2, that's a half, minus 1 over square root of 2 times 1 over square root of 2. This inner product is 0. So we found a second vector which corresponds to right and left, a candidate, if you like, for right and left. And what's more, you'll notice that this vector also has the property that the probability for it to be up and down is equal to a half for each one. Why? Because the square of this is 1/2, and the square of the magnitude of this one is 1/2. So we have a nice symmetrical relationship between left, right, and up and down. Incidentally, it's kind of interesting. Supposing, where's my eraser?
Under your paper.
It's kind of interesting. I've written right and left in terms of up and down. I could, of course, write up and down in terms of right and left. Let's see what we get. If we add these two equations, the downs will cancel, and we'll just get up. We'll get 2 over square root. We'll get square root of 2. That's 2 over the square root of 2 times up equals right plus left, and then divide by square root of 2. And we'll find that down is equal to right minus left over square root of 2. So you see there's a complete reciprocal relationship between them. If we began our experiments with our apparatus along the x direction, we might have started with left and right and come to the conclusion that up and down are combinations of left and right. Okay, that leaves in and out. What about in and out? Is there a third pair of vectors in and out which stand in the same relationship to right and left and to right and left and to up and down as they stand to each other? Is there a third combination which is symmetrically defined? All right, let's put it up here. We have up and down, and they're orthogonal to each other. We have right and left, right, which is equal to 1 over square root of 2. We can write it as up plus down. And left, same thing, 1 over square root of 2 times up minus down. We also have right, left equal to 0. Moreover, we have something that I'm not going to write, but I'll say it anyway. If you start and write, and you say, what's the probability for up and down? It's 1/2. If you start with left and ask what's the probability for up and down, it's 1/2. What happens if you start with up and down? What's the probability for right and left? Well, it's also 1/2. We know that's 1/2 from the physics of the situation, but it's also true that when I rewrite up and down in terms of right and left, the coefficients are also 1/√2. So they're nice and symmetrically related to each other. All right, so that leaves us with the last possibility, or the last perpendicular direction, in and out. Okay, so let's try to guess. It's going to have an up, and it's going to have plus a down. But there's going to be some coefficients here. We don't know what those coefficients are yet. What do we know about the coefficients? They're complex in general. In general, they're complex.
Their modulus, well, squared has to be 1/2.
The square has to, the magnitude of this square has to be 1/2. We also know that the coefficients here have to be such that in and out are perpendicular to each other. And we also should find that if we rewrite in and out in terms of left and right, the coefficients should also have modulus 1/2, just by symmetry. Turns out that's enough to determine them completely. I'm not going to prove it. That's a homework assignment. It's a nice homework assignment. Let's see what the requirements are. The requirements are that in out equals 0, that both in or out, when written in terms of up or down, should have coefficients whose magnitude is 1/2. Squared magnitude is 1/2. And also, when written in terms of left and right, the same corresponding coefficients here should have magnitude plus or minus 1/2. That is enough to determine the coefficients in terms of up and down with a small ambiguity which is not interesting. I'll tell you later what that ambiguity is. It has no physics in it. First of all is the overall sign of the vectors. That has no physics in it, as we'll see. We'll find out. All right, what is the solution? The solution is 1 here and I here with a square root of 2. We have to put a 1 over square root of 2 and a 1 over square root of 2. And out is the same thing minus I over square root of 2 down. Let's write it in terms of column and row vectors.
Should that be an I over square root of 2 on the in vector? Let's take a 1 at least.
Well, I have I there. Is that what you're asking? Yep. I actually had it right. It was 1 times I. Good. All right. We can write these in terms of column vectors. Let's write the various column vectors. Up. What would you write for up? Well, we could write 1, 0. Now, up is just up with no down component. Down is just 0, 1. A 1 in the down place and a 0 in the up place. What about right? That's equal to 1 over square root of 2, 1 over square root of 2. Left, that's equal to 1 over square root of 2 minus 1 over square root of 2. And now let's put in. In is 1 over square root of 2, I over square root of 2. and right, out is equal to 1 over square root of 2 minus I over square root of 2. First question, is this orthogonal to this? How do we check? We take this times the complex conjugate of this plus this times the complex conjugate of this. That's the rule for calculating inner products. We could construct the row vectors. We don't need to. Oh, no, we don't need to. Remember that the row vectors have complex conjugate entries. All right, but it's easy enough to do just the inner product. The inner product is the sum of the products of the entries times their complex conjugate. All right, so one of these has to be complex conjugated. What's the product of this with its complex conjugate? 1/2 times 1, it's just 1/2. So this one times this one gives you a 1/2. And how about this times the complex conjugate of this? Minus 1/2. Minus 1/2. Minus I over 2. What's the complex conjugate of I over square root of 2? Minus I over square root of 2. So we have to multiply minus I over square root of 2 times another minus I over square root of 2, which gives us minus 1/2. I times I is minus 1. So that gives us minus 1/2. And if we add them up, we get 0. So yes, these two are orthogonal to each other. The magnitude of the coefficients here, the square of the magnitude of the coefficients are each equal to 1/2, which proves that if you're in the in state or the out state, the probability of being up or down is 1/2. How about the probability of being left or right? How might you figure that out?
Why isn't I times I equals I squared?
Say it again.
I times I equals I squared?
Definition of I is that it's the square root of minus 1. So I times I is always minus 1. I is not, oh, sorry, this I is not in, no. This, okay, I and out, right and left, up can stay the way it is, and down. And now go back throughout all of the pages and change it. Not important. Actually, we could have changed it more easily. Just change this I to capital I, but that would be bad form. Bad form. Okay.
Is there anything about this coordinate system that could imply a left or right-handed coordinate system, like A cross Y equals Z?
Very, very good question. The answer is yes, but we'll come to it. Yes, that's a very, very good question. What is it that's in here that is telling us that it's a right-handed coordinate system rather than a left-handed coordinate system? And I didn't want to go there yet. We'll come to it. We'll come to it when we explore the Pauli matrices. But for the moment, we're just, we're sort of guessing our way, bumbling through, trying to find vectors which describe various states of the system. Okay, this is my proposal, if you like, my best guess at the moment for what the states up, down, those are base, you start with those. In terms of those, what right and left are and what in and out are. Now, what you could do, we saw that you could rewrite up and down in terms of left and right. I showed you how to do that. And that means you could write I and O in terms of left and right. You could check what the coefficients are. I hesitate to do it because I'm sure I'll bumble it. On the other hand, I'm tempted to do it because I'm sure I'll get it right. I'll take one shot at it. One shot, and if it doesn't work out, okay. Up is left plus right. Down is left minus right, with a square root of 2. So let's see if we can figure out what in is first. Let's just do in. In is 1 over the square root of 2 times up. What did I say up was? Up, I said, was left plus is left plus right, but with a 1 over square root, with another 1 over square root of 2. So that gives me a 1/2. That's left over 2 plus right over 2. That's scary. And then plus I over square root of 2 times down. Anybody remember what down was? Left minus right over the square. So that gives me another, that will give me left right over another square root of 2 minus left over another square root of 2. All right, so the whole thing looks like
There in your second term.
Second term has 2 1/2. Should have only one.
The second term. No.
Here?
No.
No,
Go back.
one left.
That one right there.
Right there.
You got half and then got
There you go.
2.
Yeah.
yeah. And this can just be a 1/2 with a square root of 2 and a square root, and that's gone away, right? Do I have it right? Good. Okay, so what do we get? We get a coefficient times left. All right, so here we are. I is equal to 1/2 minus 1 minus I over 2, is that right? 1 minus I over 2 times left plus, I think it's 1 plus I over 2 times right.
You mean like O instead of I there?
Here?
Are we doing I or O?
I think we were doing I, but I'm not sure. Doesn't matter. I think we were doing this one. Up is left plus right, and down is left minus right with the same I. So I think that's right. Okay, now, what's the magnitude of the two coefficients here, then times their complex conjugates? Let's check that. I don't see any square roots of 2 in this thing. Do you see any square roots of 2 in here? You might have expected some square roots of 2, huh? Nevertheless, I maintain that if you take this times its complex conjugate, I hope to God it's true. I maintain that if you take this times its complex conjugate, you will get 1/2. Let's check it. It's 1 minus I times 1 plus I over 2 times 2 is 4. 1 minus I times 1 plus I, oh praise the Lord, is 2. Is 2 over 4, which is equal to 1/2. In other words, this coefficient here, although it doesn't contain any explicit square root of 2, it times its complex conjugate is equal to 1 over 2. So the magnitude of this complex number here is 1 over the square root of 2. It's written in a form that you don't see any explicit 1 over square roots of 2, but the magnitude of this is 1 over square root of 2, and so is the magnitude of this. The implication is that if you started in the state I into the blackboard, and instead of measuring up or down, you measured left or right, the probability would be 1/2. All right? So we found 3 mutually related, they're not orthogonal to each other. Up and down are not orthogonal to left and right. And they're orthogonal to each other, but they're not orthogonal in the vertical direction. But each one, if expanded in any of the others, would have coefficients whose magnitude was 1 over the square root of 2. So they're symmetrically related in that sense. And what this means, in effect, is that if you start with any one of them and measure the other component, if you start with up or down and measure sigma x or sigma y, you'll get probability 1/2. No matter what you start with, any one of these 6 combinations, and measure a perpendicular combination, you'll always get probability plus or minus 1/2. Now, I've put in here some postulate about what probabilities are without telling you, but I think we're coming along pretty well. We have some mathematics here, which is telling us that these 3 collections of pairs of vectors are nicely symmetrically related to each other. And that, well, that's the most important fact. Yes. Yeah. Yes, sir, Kevin.
You have 3 sets of mutual orthogonal bases for 2-dimensional vectors.
No, we don't have to. No, this is orthogonal to this. Oh, I'm sorry.
3 sets of
3 bases.
for
Yeah.
2-dimensional vector space.
That's 3 bases at angles with respect to each other.
And so why 3?
That's a good question. The question is, could we find, oh, excellent question. Could we find another double? Let's call it big and little. No, we already used little, L. Fat and skinny, yeah. Fat and skinny. Can we find another pair such that fat is orthogonal to skinny and the inner product, that's what it actually came down to, or that the expansion coefficients of each one in terms of the other kind of basis are always equal to 1 over square root of 2, or always 1/2 in magnitude? The answer is no. There is no no 4th combination that's in the same relationship. Now that's not obvious. That's not obvious.
That's not because we live in a 3-dimensional world.
It is the fact that we live in a 3-dimensional world. It's exactly the fact that we live in a 3-dimensional world. Right. It's exactly the fact. It's the statement that the 3 dimensions of space can be represented in 2-dimensional vector space terms. All right, let me tell you something else which is true. If I give you a column vector, let's say a column vector, alpha 1, alpha 2, or just the coefficients of expansion, alpha up and alpha down, if you like. The question is, how much freedom is there in the alphas such that it doesn't change the physical nature of the state? How much freedom? Does every combination of alpha up and alpha down correspond to a different state? The answer is no. First of all, the total probability has to add up to 1. So that's one constraint right there, that alpha up star alpha up plus alpha down star alpha down is equal to 1. There's another fact that we have not got to yet, but we will find that every physically observable quantity always associated with a state always involves an alpha times a complex conjugate alpha. We will find that. We'll find it. We won't put it in. It will emerge as one of the consequences of the postulates. But what it says is that if you multiply both of the alphas here by the same phase factor. Does everybody know what a phase factor is? A phase factor is a complex number of the form e to the I theta of unit length. It doesn't change the magnitude of either coefficient here, that if we multiply every entry by the same phase factor, it doesn't affect anything. That means that if I were to just give you two complex numbers here, there are two redundant pieces of information that really don't have anything to do with the physical character of the state. The first is the overall magnitude, because the overall magnitude should always be such that the sums of the squares of these add up to 1. So that means there's one, call it a constraint if you like, and a redundancy. The redundancy is that if you multiply both entries by the same phase factor here, it also doesn't change the state. So then you could ask, how many independent variables are there which characterize the state of the system, of this system? How many of them are there? Well, let's count. There are two independent variables. If we don't worry about either of these constraints here, how many things does it take to characterize two complex numbers? 4. 4 real numbers, right? But now one of them doesn't count because we have to satisfy the constraint that the total length of this is equal to 1. One of them doesn't count, but also another one doesn't count because the overall phase, if we were to multiply everything by the same phase factor here, it also doesn't count. Doesn't change the nature of the state. So 2 of those 4 parameters are irrelevant to the physical character of the state. How many does that leave over? 2. 2 real numbers. How many numbers does it take to characterize the direction of a unit vector? 2. What are they called? Longitude and latitude or something like that. Just the direction of a vector can be characterized by 2 angles. These 2 pairs of numbers are the same. The fact that it takes 2 real parameters to describe a 2-component vector like this is closely related to the fact that it takes 2 real angles to describe the direction of a 3 vector in ordinary 3-dimensional space. If we would have added more components here, it would have been more complicated. So yes, there is a deep connection between the fact, very deep connection between the fact that we only find 3 independent combinations like this. Where are they? 3 independent combinations, and that fat and skinny never, we can't find fat and skinny basically, they won't be there. Not without increasing the dimensionality of the vector space. That is, in fact, very deeply connected to 3 dimensions of space. Yeah. If space was 9-dimensional or something like that, we would not be able to represent the directions of a little arrow in it quantum mechanically by 2 components vectors. We would need more components. Yeah.
It seems like just physically you would take 3 because 2 to specify the direction, and then you've got to say whether it's +1 or -1, right? Oh,
No. The plus one. No. The +1 and -1 are
inherent in the basis, right?
Yeah.
So how does this scale up if you had like 3 complex numbers in your vector space?
I mean, if you wanted to study some higher dimensional space, oh God, we have to figure it out. I don't know. The question is how many directions, how many parameters are there to, yeah, it's more complicated. That one I'm not going to try now. Right. I did. I gotta tell you, I got really scared when I realized that we weren't going to get any square roots of 2 by doing this.
The experiments you described agree with this math, and this math is based on or correlates with there being 3 space.
It is, yes. All of what you say is true.
If you said there's 9 dimensions, would this experiment still agree with
There would be a version of it. There would be a version of it. It would be more complicated, and you couldn't describe the spin of a particle by just a thing with two components like this. It would take more components.
what kind of apparatus would you use?
Spinor theory. Similar things. Similar things. Don't try to look. This is enough for now. Understanding this. If we went to four-dimensional space, we would need four-component objects, but it grows in, 3 to 4 would be, yeah.
You said the states sort of correspond to unit vectors in this vector space. What about the other? What about non-unit vectors? Are they of any interest here at all?
Well, of course, if you add 2 unit vectors, you can get a non-unit vector. You can. But then the rule for the states of a system are divided through by an overall factor until it's normalized. They have the same significance as probability distributions which don't sum up to 1. You can always go back and say, if somehow, somewheres along the line, I got some answers for probabilities that added up to something greater than 1, well, I would just divide through by the total probability to define normalized probability distributions. So in intermediate steps of calculations, there might well be the presence of vectors which are not normalized. But at the end of the day, the states of a system are normalized vectors. Normalized vectors and with no memory of what their overall phase is. There's a mathematical term for that, but we don't need it. Questions? All right, we've gone through a lot of stuff. We will make it more precise the next time when we discuss observables, in particular when we discuss what the mathematical nature of these sigma x's, sigma y's, and sigma z's are. For the moment, we just specified them sort of by experiment. You hold your apparatus this way and you measure something called sigma x. You hold it that way, you measure something called sigma y. And we used some symmetries, namely the equivalence of different directions of space, to guide us into finding expressions for the various physical vectors describing different orientations of the spin. But we haven't been very rigorous about it, and I have made no pretense of really a mathematical clear derivation of these things. Sort of seat of the pants guessing to a large extent. The next time we will make some rigorous postulates about what these things really mean and their relationship, these things, and what the relationship between them is. The vectors and the things that you measure. These are the states, but these are the things you measure about them. And the question is, what's the connection between them? Okay, any more questions about this?
Are these lectures tracking the content in the sequence that goes in the web?
I imagine they are, but I don't remember. But there's only one way that I know how to think about quantum mechanics, so I bet they are. And you know, if you're sitting through this for the 3rd time, that's your problem. Believe me, I'm sitting through it to the
Yeah. So is that phase factor that we can ignore?
Yes, the answer is yes, I think. Yeah.
Is that phase factor, are we going to be doing anything with that? Are we going to be looking at that at all?
Well, mostly we'll be saying, look, it doesn't matter. All right, it doesn't matter. Okay, so let's talk about the mathematics of ignoring something. Yeah, that's right. Yeah, yeah, that's yeah, that's true. But let's just talk about the mathematics of ignoring things for a minute. All right, a point is 0-dimensional, right? A circle is 1-dimensional. There's one parameter, an angle on it. But supposing I tell you that there's no significance to where you are on that circle. There's no significance whatever. All points on that circle are equivalent to every other point. Then you might say, well, for all interesting questions, the circle is just a point. If you can ignore where you are on the circle, then there's only one point on the circle. You're either on the circle, well, if you're on the circle, you're on the circle, there's one point. You can say the same thing about, let's see, another example. What's another example? Well, let's take this example. If you have well, what is a complex number? A complex number is a point on the plane. But if for some reason the angle of where you are on the plane doesn't matter, then the only thing that's interesting is the distance. But now supposing you have two complex numbers, and all I tell you is that when you have two complex numbers, the thing which doesn't matter is the sum of their phases. The sum of their phases, the sum of their angles. Then there is still one angle left over which may be important, the difference of the angles. So if I have two complex numbers, and I tell you, for reasons that I haven't specified yet, that the overall phase, which can just be thought of as the sum of the phase angles, if the sum of the phase angles, for whatever reason, plays no role in the physics of the situation, there is still the difference of angles there. That's exactly what the case is. The sum of the angles, of the complex numbers that go into these entries here is of no physical significance. We counted up 4 real parameters for 2 complex numbers. The overall magnitude of it doesn't count because we divide that out. That removes one of them. And then the sum of the angles doesn't count for whatever reason. That removes another one. That leaves you with two real numbers. And that's in correspondence with the 2 real numbers that it takes to pick a direction in space. So there's a lot of subtlety, but nothing very difficult. The mathematics is really easy. The mathematics of quantum mechanics is easier than the mathematics of classical physics. 2x2 matrices is very simple. Mathematics is easier, it's unfamiliar. Yeah.
There's something that's always been vaguely unsettling, which I think gets at the heart of all this, of the idea that the up and down are along a single axis, one pointing this way and one pointing that way, but they're orthogonal somehow, as opposed to
Well, orthogonal doesn't mean perpendicular in 3-dimensional space. It means physically distinguishable. It means unambiguously distinguishable. Left and right are not physically distinguishable uniquely from up and down. Why? Because if you have a thing oriented along left and you measure up or down, you might get up.
So I often think of 2 orthogonal axes as being 2 independent variables that you could vary independently.
Yes, that's right. So here you can vary independently the probability for up and down. Of course, they have to add up to 1. Right. They have to add up to 1, but ignoring the question of whether they add up to 1, you have the freedom to independently vary the coefficient in terms of u and the coefficient in terms of d. Now, the fact that they have to add up to 1 is another fact. Yeah, don't confuse orthogonality in the space of states with orthogonality in 3-dimensional space. The analog idea in phase space, or in the configuration space of a classical system, orthogonality of 2 probability distributions. Let's suppose you have phase space. or the configuration space of some classical system. Here's the phase space, X and P. And I give you a probability distribution. A simple probability distribution might be 0 everywhere except in some patch, where the probability is uniform. Okay. The analog of orthogonality of two distinct probability distributions is that they don't overlap, that they're non-overlapping, that there's no ambiguity. And that's the analog of orthogonality. Up and down don't overlap. If you're up, you're not down, and if you're down, you're not up. Right. Now, if you think about, there is a situation in which orthogonality is the same in space and in the space of states. It's the polarization of photons. The polarization of photons is a little bit different, and I didn't want to get into it because it's more complicated. Right. It would have been better if there was a different word for perpendicularity in space and orthogonality in the space of states. A different concept. I mean, it's very much what's going on here, that being oriented along right can I do an experiment which can distinguish between a spin pointing up and a spin pointing down? Yes. You can bring your apparatus over to it, detect it, and if it's up, it'll point 1. If it's down, it'll point -1, or it'll give a -1. Can you use that apparatus to tell you uniquely the difference between a spin pointing along the x-axis and a spin pointing along the z-axis? What would you do to tell the difference? What would you measure? No matter what you measure, it's not going to uniquely tell you the difference. If you measure sigma z and you get +1, that doesn't tell you anything about sigma x. It doesn't, you could have gotten sigma z equals +1 because it was pointing along the z-axis, and you got it with certainty 1, or it was pointing along the x-axis, and with probability 1/2 you got it pointing up. There's no way to tell. There's no way to tell by a single well-defined experiment whether the spin was pointing, let's say, up or r.
What if you measure if a photon comes off or not?
With one experiment, either a photon will or won't come off, and from that you cannot tell uniquely whether it was... No, you can't tell from that. It's exactly the same as measuring the spin. If you get up in your measurement, it does not tell you whether it was initially up or it was initially sideways, and with probability 1/2 you got up. Okay? So there's no unique single experiment you can do to distinguish this from this. There is an experiment that you can do to distinguish this from this. That's what makes up and down orthogonal, but down and left not orthogonal. They overlap. They overlap. And in fact, the probability that if you are in left, that you measure down when you measure sigma z, that's a measure of the overlap between them. Right? The overlap, which means in technical language that they're not orthogonal.
So, backtrack to the hierarchy thing. Originally, you said we didn't know that it was programmed up Z, but if we measured up Z and got up, we didn't have to measure anything else.
If what we're trying to do is confirm the proposition, the spin is up, or the spin, or the z component of spin is up, or the x component of spin is up. We want to confirm that. That's a single proposition. It's not two propositions. It's a single proposition. The spin is up, or the spin is up along z, or it's up along x. That's a single proposition. if the first detection measures the spin up along the z-axis, we're finished. Right. And then since the setup was set up beforehand, we know that in that case we would get the right answer. Okay. Okay. I think
Would it be fair to
Yeah.
would it be fair to summarize that point as saying that propositions are not commutative?
Yeah. 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 I mean, actually, propositions technically correspond to projection operators, and projection operators are not commutative. Yeah, it would be proper to summarize. I don't know if that summarizes everything about it, but that certainly summarizes part of that point, yeah. Depends on which order you, yeah.
So you've cautioned us about trying to visualize, okay? But so is the sigma along the z-axis or along the x-axis, isn't that a visualization that?
It is. 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 It is.
That would explain why it doesn't make sense where you measure it
Well, yeah.
and then you measure
Yeah.
again and it's in the extra.
Yeah. Yeah. No, it is. It is a visualization. Do keep in mind, though, this interesting fact that on the average, the spins, if you measure many of them, many of them, the average values do behave like components of a little vector. In particular, if you take a large number of these spins and you make sure that they're all pointing upward, and then you measure some oblique component of them with your apparatus being tilted, then the average that you'll get for the oblique component will just be the projection of the upright vector onto the oblique direction, exactly as if you were measuring the component of a vector. So the upshot is, if you have a large number of them, in many cases you can visualize with classical physics. After all, that's what classical physics is. Classical physics is to a large extent the approximation of systems which consist of many parts which all behave simultaneously the same way. So
I'll try one more question. Is there any, looking at the properties of the model you described, is there any relation between that and the notion of gauge invariance?
I suppose. I suppose there is. You'd have to be more specific than that. Gauge invariance does have to do with these phase factors here. Yeah, it does have to do with them, but it does have to do with them, but we can't get into that right now.
Actually, one thing that I find myself getting confused about, but I think I see it now, is that we're calling a measurement, and the tendency is to think of a measurement in the classical sense, like here comes, say, a particle, and we're going to measure some property. But it's not like that, because we can't really say what the value was before we did the measurement. We can only say what it is after we do the measurement. Right?
But then, once we measure it, we can measure it again, and the same thing again, and there will be consistency.
I mean, we put it in a certain state, and we know what that state is. And if we do the same exact preparation over and over and over again, then we get this distribution.
Yeah. That's right. You can't always think that a system has a property and it's just your job to find out what it is. Yeah.
For more, please visit us at stanford.edu.